Good evening. We're going to talk about factoring. And really, this is a crash course in factoring. But let's start off with why do we need to factor in the first place? Well, factoring in the first place is going to make it possible for us to solve a quadratic expression without using other means. Now, there are two other ways that we can solve a quadratic expression, one of which is called completing the square, which you haven't learned yet. Another is using the quadratic formula, which again you haven't learned yet. And we will learn those next week. However, the easiest way to solve a quadratic by far is if you can factor the quadratic expression first. So we're going to take a look at the 5 ways of factoring, and we're going to start with our factoring checklist. Now, when you are factoring, you need to go through this checklist from bottom to top every time that you are about to factor. And apparently when I do that, okay. So, the first thing we're going to look for is a greatest common monomial. Then, if we have factored out a greatest common monomial, or if there isn't one, we will look for a difference of squares, followed by a square binomial. The most common factoring of all is a binomial pair of factors, plural. And finally, factor by grouping. Now, we're going to look at some basic examples of these things. We're not going to look at the hardest type of factoring possible. Just a refresher, if you will. So if we look at finding the greatest common monomial, and we have the polynomial 6x to the third minus 3x squared plus 9x, we need to ask ourselves, is there a number or a letter or both that go into all 3 of these terms? Well, I see an x, and I see that all 3 of those are multiples of 3. So that means that I can divide this expression by 3x, and that 3x will go into all 3 of these terms. So I'm going to have to divide everything by 3x. And when I am factoring, what you divide out does not disappear. It will go on the outside of our final answer. Give me a second. All right, hopefully I can find that again. All right, so we have our 3x. And now, what is 6x to the third divided by 3x? Well, 6 divided by 3 is 2. X to the third divided by x is x to the second. What is negative 3 divided by 3? Well, it's still negative. 3 divided by 3 is 1. I don't have to write the 1. X squared divided by x is just x. Finally, we have positive 9x divided by 3x. 9 divided by 3 is 3. X divided by x is just plain old x. X divided by x is 1, so it disappears. And so we're left with 3x times the quantity 2x squared minus x plus 3. And that's really the essence of factoring out the greatest common monomial. We are going to look for whatever goes into whatever is common to all 3 of these terms. For a difference of squares, 99 out of 100 times, when you're asked to factor a difference of squares, it will be a binomial. 2 terms, 1 term, 2 terms. And that binomial will consist of 2 perfect square terms, thus the name squares. And we will have to be subtracting them, and that's why we have the difference. So we have a true difference, which means subtraction, of 2 perfect square terms. X squared is a perfect square. 9 is a perfect square. And we're subtracting them. So guess what, folks? We have a difference of squares. And so all differences of squares will be factored in such a way that you will have a pair of binomials. And one binomial will have an addition sign, one binomial will have a subtraction sign. So now we are going to take the square root of both of these terms. What is the square root of x squared? X, because x times x is x squared. What is the square root of 9? Well, 3. 3 times 3 is 9. And positive 3 times negative 3 would be negative 9, wouldn't it? And so there we go. We have fully factored this expression, and this is the difference of squares. Now the nice thing about a difference of squares, and the same can be said about square binomials, it's a shortcut for factoring with a binomial pair of factors. You could still do factoring a la binomial pair of factors for differences of squares and square binomials. You cannot do it, however, for greatest common monomials or factoring by grouping. That's supposed to have an O. All right, so I get ahead of myself. All right, so now let's look at this one. So 144 is a perfect square. X to the fourth, a perfect square. I'm subtracting. 100 is a perfect square, and y to the 10th is also a perfect square. So we have a differences of squares. So same process is going to take place. We're going to have a binomial pair, and each binomial will have a different sign inside of it. What is the square root of 144? It's 12. What is the, I'm going to drop this down a little bit so it's all in one line. What is the square root of x to the fourth? X squared, because x squared times x squared is x to the fourth. So that's going to go in both binomials. All right, what is the square root of 100? Well, that's just 10. What's the square root of y to the 10th? Now, you may think that 10 is not a perfect square number, and it isn't, but y to the 10th is, because y to the 5th times y to the 5th is y to the 10th. So that's why y to the 10th is a perfect square term. And so here we go. Here's our binomial pair of factors, factored using the difference of squares. Now, the square binomial, third thing we look for, is also a shortcut, if you will. But I realize it's the least of all favorite shortcuts because it doesn't feel like a shortcut at all. The first thing you're going to have to look for is, a square binomial have to be a trinomial. It's got to be a trinomial. And it's a trinomial where the first term and the last term are both perfect squares. But that's not all. This middle term, this linear term right here, has to be 2 times a times b. So let me write that down really quick. So we know that the linear term has to be 2 times your a term times your b term. Well, what is your a term? What is your b term? Here we go. So a square binomial will be factored in such a way so that you have a binomial squared. And the sign inside that binomial will match the sign of the linear term, that negative there, and it will be squared. All right, so your a term is going to be the square root of your quadratic term. Your b term is going to be the square root of your constant term, your c term. So what is our a term for this possible square binomial? Well, the square root of x squared is x. Again, we have subtraction. The square root of 9 is 3, and that whole thing has to be squared to be a square binomial. But we're not done yet. We're not sure if this worked because there are definitely imposters for square binomials. So we need to double check. And we know that 2 times a times b has to equal, in this case, 6x. So we have 2 times our a term, and our a term in this case is x, times our b term, which is 3. 2 times 3 is 6, so we do get 6x. So we do have a square binomial. Now, it is not acceptable for a square binomial to be answered like this. There's a simpler way. And so you are expected to have an answer that looks like this red answer, if it would turn red for me at all. All right, there you go. So same idea here. So 9 is a perfect square. X squared is a perfect square. 16 is a perfect square, and y squared is a perfect square. So we may have a square binomial. So I'm going to take the square root of the first term. So 9x squared, if I take the square root of that, I get 3x, plus the square root of 16 is 4, the square root of y squared is y, and so that has to be squared. Now that certainly looks like the answer, but we're not done yet. We need to make sure that the linear term is 2 times a times b. So we know that 2 times a times b has to equal 12xy. So let's look at our a's and b's. Our a term is right here. It's the 3x. Our b term is this term right here. That is 4y. 2 times 3 times 4 is, oh shucks, this is not, it doesn't work, does it? So therefore, this is not a square binomial. Oh, sorry, yeah, square binomial. Oh, you get the idea. It's not a square binomial. All right, great. Obviously, I didn't mean for that to happen, but I'm glad that it did. All right, so the most common way to factor is factoring a binomial pair of factors. All right. So this is the proverbial divided rectangle or the factor sum table. So if I have, I know that, that's not what I want. So I know that this rectangle right here has to be x squared. And I know that because x squared is the first term, the quadratic term in this polynomial. Well, what times what is x squared? Well, x times x is x squared. That's not what I wanted. There we go. X times x is x squared. Well, what times what is 24? Well, how about 3 times 8? 3 times 8 is definitely 24. So that would make the area of this rectangle right here 3 times x, which is 3x. That would make the area of this rectangle right here 8 times x. Well, 8 times x is 8x. 8x plus 3x is 11x, but that's not what I have in here. And incidentally, 8 times x, or 8 times 3 is not negative 24 anyways, right? So since this is negative and this is negative, negative 8 times negative x would be negative 8x. So 3 times negative 8 would be negative 24, so that worked out okay. But here's the problem, folks. 8x minus, or negative 8x plus 3x is negative 5x. That's not the linear term. So we know this didn't work. We need to try something else. How about negative 6? Negative 6 times 4 would still be negative 24. Negative 6 times x here would be negative 6x. 4 times x would be 4x. And this time, negative 6x plus 4x is negative 2x, so it worked. So what we do is we take this side length here and we just put it together. So that side length would be the x plus 4, and we know the area of the whole rectangle will be base times height, so the height is simply x minus 6. Voila, it's the same thing. Now, I prefer a factor sum table, quite frankly, because it allows me to do this. I get to write the factors, and we're looking for factors of negative 48. We're always looking for factors of the last term, the c value. And I know that negative 12 times, what shall we say, 4. Well, that is negative 48. If I add those two numbers together, I will get negative 8. That's not what I want. Okay, so what about positive 12 and negative 4? Well, that would give me positive 8. Not better. So I need to pick something else. How about 16 times negative, I don't know, 3. 16 minus 3 is in fact 13. We have a winner, so we just put these two terms in separate binomials. And we know that x times x is x squared, so we're good. Finally, factoring by grouping. In its easiest, most essential form, we are taking the same binomial and we're multiplying it by different monomials. So in this part right here, we have 3 times x and 3 times y. Over here, we have z times x and z times y. Notice how we're multiplying 3 to x and y. We're multiplying z to x and y. Well, why don't we just do this? Since that's the case, we can just get away with taking the, taking the terms on the outside, putting them into one binomial together, and keeping the x plus y over here. And so we still have 3 times x, 3 times y, z times x, z times y. So there you go. Now, a slightly more difficult version is if you have opposites that are already factored apart. Well, here we have x minus y, but over here we have y minus x. The easiest way to deal with this problem is not to have 20-point font when everything else is 9 and 8. All right. The easiest way to deal with this. Oh, jeez. Oh my God, this is driving me crazy. Here we go. Is we can factor out a negative 1 from this second binomial. Now, when we factor out a negative 1, remember from your greatest common monomial that negative 1 doesn't disappear, it gets applied to the outside. Negative 1 times z is negative z. And if we divide both these terms by negative 1, the signs will change. So by doing that, we will end up with negative z times x minus y. Oh, look, the binomials are now the same, which goes back to this case right here. So that means we can get away with taking the things that are on the outside and putting them into one binomial, and then take the common binomial, and voila, we've done it. Finally, the last form of factoring, the last factoring I want to talk about with grouping is when nothing is grouped together. Well, then it's time to group things together and see what happens. I'm going to just put those together. I'm going to put these together, and let's see what happens. Is there a common monomial that goes into both of these terms, rs and 5r? Well, yes, there is. R goes into both of them. So we have r times s plus 5. Well, how about the second binomial? What goes into st and 5t? Well, t does, of course. So we can factor out a positive t. And don't forget, you can also factor out a negative 2 if you need to switch signs. And we will be left with s plus t. Oh, no way. That means it's the same as all the other problems. So we have the quantity r plus t times the common binomial s plus t. I feel like I've done something wrong here. Yes, because this should be a 5, because 5t divided by t is simply 5. It's not t. I got t on the brain. It's a little warm for t, don't you think? All right, so finally, we're doing all of this stuff so we can solve a quadratic expression. To solve a quadratic expression, you'll remember from yesterday that a solution to a quadratic equation or a quadratic expression is the x-intercepts. And at the x-intercepts, the y value is in fact 0. All right. And we need to have this in factored form. Well, what times what is negative 12? That adds to negative 4. Oh! No. 6, yeah. Negative 6 times, let's make that a positive, shall we? Don't you love typos? So we know that negative 6 times, we do need this to be negative. So, and this is going to be wrong. So we have x times negative 6 times x plus 2. Negative 6 times positive 2 is negative 12, but 6 plus 2 is negative 4. Okay, and this is still equal to 0. Now, if we're multiplying two things together and we're getting 0, that one of those two things has to be 0. So what you're going to do is you're going to set each of the binomials equal to 0 and treat them as completely separate problems. All right, well, subtract. So on this one, if I subtract 6 or add 6 to both sides, I'll just get 6 is equal to x. Oh, that's excellent. On this side, we'll subtract 2 from both sides, and I'll get x is equal to negative 2. So that means the x-intercepts are at 6 and negative 2. And that's also the solutions. So those are the solutions for this expression. Remember, has to be equal to 0, has to be in factored form. All right, so I realize we've condensed a ungodly amount of factoring into about 15 minutes. Good luck. And good luck to me for finding where the pause button is.